started to work on Galois theory, so we had introduced the Galois extension, so finite separable model extension is called the Galois extension. We had the Galois group. This was a set of all K automorphisms of L, so automorphisms of L which are identical on K, and if L over K is Galois, we had seen that the number of elements in the Galois group of L over K is equal to the degree of the extension. No, because we had seen this was because by the theorem of the primitive element, this will be a simple extension, and then it acts simply transitively on the roots of the minimal polynomial of the extension. So then we had this proposition, which I said is useful to understand the Galois group. So if L over K is a Galois extension, and we have two elements in the bigger field, then the Galois group will send one to the other if and only have the same minimal polynomial. So there exists an element phi in the Galois group of L over K, which sends A to B if and only A and B have the same minimal polynomial. Over K. And we had, so this was not completely obvious. We had used this to prove the following theorem, which we will see today is a big part of the proof of the fundamental theorem of Galois theory. So if L over K is a Galois extension, then if I look at the set of all elements in the bigger fields, which are fixed by all elements in the Galois group, then this is equal to K. So if every element in the Galois group of L over K fixes, sends A to itself, then A already must lie in K. Okay. So this is, I think, more or less where we were. And now I want to introduce the Galois group of a polynomial. So what I mean by this is this will be actually strictly speaking the Galois group of a polynomial over a field K is the Galois group of the splitting field of this polynomial over K. So definition. So let f into x be a polynomial. So let L be a splitting field of f over k. So then the Gottshe group of f is strictly speaking over k, but usually we assume we somehow remember what k is just the Gottshe group of L over k. So the Gottshe group of polynomial is just the Gottshe group of the splitting field. Okay, and so now, so one will want to study polynomials or the solutions of polynomials in terms of this Gottshe group. Obviously, one needs to be able to say something about the Gottshe group without knowing what the solutions are. So first we have the following. So we want to describe this. And so what we find is that the Gottshe group is a subgroup, or is isomorphic to a subgroup of the permutations of the zeros of this polynomial in its splitting field. It's just a subgroup of the permutations of the zeros. Okay. So proposition. So let f be polynomial k of some positive degree and bigger than 0. So let R be equal to the set of zeros of f in its splitting field. Then we have first statement is these are two quite different statements. So the Gottshe group of f, which strictly speaking is the Gottshe group of f over k, is isomorphic. But that's naturally isomorphic to a subgroup of the symmetric group on these zeros, on these roots, and the number of elements in the Gottshe group of F divides n factorial. Okay. So this is actually not quite clear why I put this together in one position. The second statement is something quite different. So if all the roots of f are simple, you see here we don't make any assumption f could be anything. If all the roots of f are simple, then f is irreducible if and only if the Gottsche group acts transitively on the roots. So if all roots of f in L are simple, then we have that f is irreducible as a polynomial in Kx. So the original polynomial over the original smaller field is irreducible if and only if the Gottsche group of L over K acts transitively. on R. Okay, so we somehow want to. So let's try to prove this. So first, the first statement.
Equation about the second point is when we say the gamma group of L over K act transitively on R, it means we can find a transitively action, or the action we define before is the action who act.
Yeah, I mean the so okay, so it is the action that's given to us. The gamma group is a group of so we'll see in a moment. But I mean, the gamma group acts on the elements of L. No, and I can, as you see in a moment, the restriction of this action on L becomes an action on R, and this action is transitive. So it's just, I mean, the gamma group is just a group of K automorphisms. So it sends every element of L. So every element of L is sent to another element of L. The elements of R are some particular elements of L, and so this is the action. It's not that we can find an action. I mean, that the given action does this. It's the same as, and it's also the same as saying the action that we have said here. It's isomorphic to a subgroup of this, which means it acts on S of R. And let's see how. So by definition, the gamma group of F is equal to the gamma group of L over K. So, and we use this trick we have already used a few times. So if A is an element in R, so that means f of A is equal to 0, then if we take and say phi is an element in the gamma group of L over K, then if I take f of phi of A, this is, as we have seen many times, the same as phi of f of A, because remember we wrote it down. The coefficients are in K, so it just acts by this argument. We have proven this. We have seen this several times. And f of A is 0, so phi of 0 is equal to 0. So thus, and this is how one gets this action of the gamma group on R. And the elements in the gamma group send R to R. So it's not here. Where is it? Okay. So thus, if we take the restriction, phi restricted to R is a map from R to R. And certainly phi is an automorphism of, so it's an element in the gamma group, so it's an automorphism of L. So in particular it's bijective, so its restriction to R is also bijective. So this is an element in S of R. Okay, so just we restrict this action to R, this gives us this. And so in this sense, the claim is that this map, so thus we want to claim that this map restriction to R, which from the gamma group of L over K to S of R is injective, is an injective group homomorphism. So then the gamma group is isomorphic to the image of this map. So, but on the other hand, this is clear. If phi restricted to R is equal to the identity on R, then phi is equal to the identity of L, because how do we get the splitting field? The splitting field is obtained by adding to K all the zeros of this polynomial. So that means that L is just, I could say K adjoint R. So just K adjoint every element in R. So if something is the identity on K and its identity on every element on R, then it is the identity. Okay. So this is injective. So that's the chain follows. So that's the value of L over K is isomorphic to phi how to call it. So I could say Converse group L over K strictly for R, which is contained in S of R. So, and then the statement about the so we also make some statement that the number of elements in the Galois group is divides n factorial. That's here we have that so we have the number of elements of R is smaller or equal to n, because which is the degree of f. No, the polynomial has at most as many zeros as its degree. So here we have not, there could be multiple zeros or whatever. And thus we have that the Galois group, the number of elements in the Galois group of F will divide the number of elements in the symmetric group on R, because it's a subgroup, and which is R. So the number of elements in R factorial, which divides n factorial. Not because R is smaller than n. So this was the first statement. So you see, it's actually it's relatively standard. No, we just have the usual thing that by the standard trick, if we restrict an element in the Galois group to the roots, we get an element in the symmetric group on the roots, and the element in the Galois group is already determined by this element. And so we can really identify with the Galois groups just with the permutation of the roots of this polynomial. I mean, with the subgroup of the permutations of the roots. The second statement is somewhat different. Let's just look. So we assume that f has only simple roots in its splitting field L. So we first want to show, so what do we have to show? First, we assume that f is irreducible. So if f is irreducible, and we take two elements, A and B, elements in R, so zeros of f, then we have to show there is an element in the Galois group which sends A to B. That means it's transitive. So then f is, so we can always renormalize it by multiplying it by a constant so that the leading coefficient is 1. So therefore f is the minimal polynomial of both A and B over k. Because f is irreducible and it has this as a 0. So thus, by this result on extensions of field isomorphisms to simple algebraic extensions, there exists, in fact, unique, but there exists an element phi in so a k isomorphism, say C from Ka to Kb, which sends A to B. No, by the result that you have, actually, we know the unique element like this. Now, note that so as K is contained in L and A and B are both elements in L, we have Ka and Kb are both subfields of L. So they are both intermediate fields. So these are intermediate fields. So F is also, so L is also the splitting field of F over both Ka and Kb. And then we had this result about the extension of field isomorphisms to splitting fields, which says that our given psi here can be extended to the homomorphism from L to F. So by extension to splitting fields, there exists a phi from L to L. So an isomorphism with a phi restricted to Ka is equal to this psi from Ka to Kb. As psi itself is a K isomorphism, this is also a K isomorphism, so that means that psi is an element in the Galois group. So thus, psi is an element in the Galois group of L over K, and by definition, phi of A is equal to psi of A is equal to B. Okay, it's relatively. I mean, we had similar arguments many times, and it works quite simply here. But one, has to know how to use these tricks. So now for the converse. So now let's assume that F is actually reducible, and we want to show that this cannot happen. So actually we will assume conversely, assume F is reducible in Kx, and say this group, but the Galois group still acts transitively. And here it says that, I just wiped it out, that this cannot happen under the assumptions, but the assumption was that F has only simple roots, so we have to see that then F cannot have only simple roots. So, F is reducible, so we can write, so let G1 and G2 be 2, so in X, be 2 irreducible factors of F. And so these are irreducible factors, so they have positive degree. So as F splits, also these split over L, and so we find some zeros. So that A1 is 0 of G1, and A2 is 0 of G2. Obviously, these are also both. No, these are both also, these are both also zeros of F. So then, by our assumption that the Gara group acts transitively, there exists an element phi in the Gara group of F, so which is the Gara group of L of K, such that phi of A1 is equal to A2. But now we use once again this stupid trick. These are polynomials with coefficients in K, so therefore we have 0. So G1 of A1 is equal to 0. So this would be equal to G1 of A1. That stays 0 if we apply phi to it. And this is the same as G1 of phi of A1, no, because it's as usual, and so this is G1 of A2. So that means that A2 is also 0 of G1. But we have assumed that G1 and G2 are irreducible. We can assume that they are monic by dividing by a constant. So that means that the minimal polynomial of A2 is G2. So, but G2 is the minimal polynomial of A2 over K. Thus, the minimal polynomial will divide any polynomial which vanishes at A2. Thus, G2 divides A1. Obviously, I can also, what? G1, yeah, okay, so that was G1, yeah. Obviously, that's what I meant. There was obviously nothing particular how I ordered them. The same holds true if I exchange the role of 1 and 2. So in the same way, G1 divides G2. So thus, if they're both monic, G1 is equal to G2. So this means, thus it follows that G1 squared divides F. So that means F, so that means that every 0 of G1 is a multiple root of F. So G1 has multiple, so F has multiple roots. Okay, so this was this statement. You can see the arguments were quite. Yeah?
We use the fact that F has multiple roots just for the converse.
No, we had no. So in the converse, so here we have made an indirect argument. We have said f is OO. So so let me see. So in the other case, we assume that f has only simple roots.
Yes.
So for the so the idea is, so here we make the converse. So we want to say if the theorem is false, then it has multiple roots. For the other direction, we assume it has simple roots, and we want to claim that the result holds. Now I don't remember where I used it. Obviously, one needs to use it because otherwise this theorem is false. So yeah, it's not so evidently. So let me see where on. I mean, obviously, otherwise it could have been that A is equal to B, but that by itself doesn't make a big difference. Well, I think that's okay. So the statement, I don't think one needs that f has only simple roots in order to draw the one conclusion. One only needs it for the converse. I mean, I effectively don't use it, and but I mean, the proof is very simple. I don't think I made a mistake. So just in that we don't need it for that. Okay. So it's only for the if and only if. So one direction is holds without that assumption. But otherwise, obviously, if it has multiple roots, so if you know, you can always have that this thing is reduced. You know, if you just have a square of something, it still acts transitively on the roots. You know, if you take f squared, then the Galois group just acts in the same way as, you know, the Galois group of that will act in the same way as it acts just on the thing of f. I mean, the splitting field of f squared is the same as splitting field of f, and the Galois group is the same. So you see that. You know. But you need, for the converse, you need this statement, but not for this. But maybe I could have stated it. I could have said this in the statement, but no. Okay, now I didn't. Okay. So I wanted to. I mean, maybe it's nonsense, but I still want to. So I've said two quite different things about this Galois. So so if you have the Galois group of the, so for a simple algebraic extension, we somehow take so I want to say that we have this, we have in some sense described this Galois group here of polynomial in two completely different ways, and I want to just make sure that we understand this. And these two descriptions are also usually for quite different purposes. And so let me so just now we described it as a subgroup of the permutations of the roots of the polynomial. So if you have a polynomial, we look at the Galois group of the polynomial. Then it's the Galois group is in a natural way a subgroup of the permutations of the roots of this polynomial in the splitting field. Okay, so mark. So let L over K be a Galois extension. So we have described the Galois group of L over K in two quite different ways. So the first one is what we did last, namely, so Galois of L over K is equal to the Galois group of F, where L is the splitting field of some polynomial F in X. No? We know that if it's a Galois extension, it's a splitting field. I mean, the bigger field is a splitting field of some polynomial. And the Galois group of A, this is what we had also called the Galois group of F. Then, so we know, or maybe until now, okay, maybe this is still not, so this is still general. We know what? So if n, so we have two numbers here, so let n, small n, be the degree of F, and let large n be the degree of this field extension. Okay. So these have not very much to do with each other. So we know that the number of elements in the Galois group of this F is equal to the degree of the field extension. Okay? So not very much to do with this. And so now we have these two different descriptions. First, so let this we just had R be the set of roots of F in L. Then the Galois group of F is isomorphic to a subgroup of S of R. And we note that the number of elements in R is equal to n. No, because this is a Galois extension, so the polynomial F what? No. Anyway, forget. Okay, so we have this. On the other hand, we can look, we also have used already many times, and this is the first thing we did, is that we use the theorem of the primitive element to see that this is a simple algebraic extension, and then the Galois group is described in terms of permutations of the minimal polynomial of this element, of this primitive element. So as L over K is a finite separable extension, we know there is a primitive element. A in L. So that means L is equal to K of A. So now let G be the minimal polynomial of A over K. Then the degree of the field of this minimal polynomial is equal to the degree of this field extension, which is n, large n. No? So this is usually much bigger than the small n. And if I look at the roots, sigma, the set of zeros of G in R, then we know, as this is the number of roots is also equal to n, because it's a Galois extension, you have an irreducible polynomial, it splits and it has no multiple roots because of separatedness. And so the Galois group of F is the subgroup, is again isomorphic to a subgroup of S of the symmetric group on this set of roots of this polynomial G, acting simply transitively. On sigma. This is how we actually showed that the number of elements in the Galois group is equal to the degree of the field extension. So therefore, the Galois group here of F is described in two completely different ways as a subgroup of a symmetric group. Here of the number of the roots of the region F, and here of the roots of this minimal polynomial of the primitive element. This somehow serves completely different purposes. So here, this we use quite often when you want to prove a theorem, because it's very nice to work with simple algebraic extensions. And so then we use a primitive element, and we know we have a simple algebraic extension, we can work with that, and in terms of the primitive element. But if we want to instead study the Galois group of a certain given polynomial f, then it's basically impossible to find out what this primitive element will be, and how, and to find the zeros of this minimal, and what its minimal polynomial is and what its zeros are. So we will actually never, essentially in concrete cases, we will never be able to explicitly say what this description is. So this is good for proving theorems, theoretically, and this is what one uses when one wants to study any example. Okay, so it's good that we know both of them. Okay, so now let's look at a few examples. What time is it? Okay. So maybe one we have already seen, but we can just follow it through. So as an example, so if we take f equal to x to the 3 minus 2, so as polynomial coefficient q, then we claim, you already said it, the Galois group of f will be equal to S3, by which I mean if I somehow number the zeros of this polynomial 1, 2, 3, then it permutes them just arbitrarily. And so we know f is irreducible, and so L equal to Q third root of 2 e to the 2 pi I divided by 3 is a splitting field. And we have already seen that the degree of L over Q is equal to 6. As this is a polynomial of degree 3, we know that the Galois group of f is a subgroup of S3. But it has already 6 elements, so it must be equal. but it has 3 elements. So they okay. So let's also look at this other example that we were looking at. So f was equal to x to the 4 plus 1. I claimed that this is reducible, and maybe it's an exercise, anyway, assume you know it. So the claim is that in a suitable sense, the Gamma group of F is isomorphic to Z mod 2Z plus Z mod 2Z. Okay, and we can precisely describe how. So we know that if alpha, say, equal to e to the 2 pi I divided by 8, is one of the zeros, then we can write f as x minus alpha times x plus alpha times x minus 1 over alpha times x plus 1 over alpha. So we have the splitting, we had seen this before. So it already splits here. So thus this Q of alpha is a splitting field of f over k, f over q. And we see it's a simple algebraic extension because it's just obtained by sending alpha. So as q alpha over q is a simple algebraic extension, and f is the minimal polynomial, we get that the degree of q alpha over q is equal to 4, which is therefore also equal to the number of elements in the Gamma group of f. But actually, even if we wouldn't know, well, okay. So, but we can see, I claim we can see it. So the map, we can check that alpha maps to minus alpha. So the map, obviously, that means its identity on K, on Q, sends alpha to minus alpha, and then correspondingly all polynomials in alpha in the suitable way. I mean, if you have so that means if I have a polynomial in alpha with coefficients in K, and it's sent to the same polynomial with minus alpha, and alpha maps to, say, 1 over alpha. These are both elements in the Gamma group of q alpha over q. So you can either directly see that this defines a homomorphism, that it's compatible with addition and multiplication if you do this, and then apply this to polynomials. Or you can also, if you want, invoke a theorem that if you say that you have if you have an irreducible polynomial, then, so if you have an irreducible polynomial with coefficients in the smaller field, then the elements in the Gamma group can send any root to any other root. Any root, and so this means there is an element for every element here, for every, for every, anyway, no, this is simple algebraic expansion. There's an element in the Gamma group which sends alpha to any of these. So in particular, it sends, we have an element here which does this, an element which does this. And these two operations, you can see that they commute. These two actions, these two elements in the Galois group commute. Whether I first send alpha to minus alpha and then to 1 over alpha, it's the same as if I do alpha, which commute. So they define, and obviously if I apply this homomorphism twice, it's the identity. So they define a subgroup of this Galois group, which is isomorphic to Z mod 2Z plus Z mod 2Z. No, just the subgroup generated by these two elements. No, which I just say, this, the subgroup has 4 elements. No, either you apply. So it's either the identity, it's this, and alpha goes to the composition of these two, which is 1 over minus alpha. And this group is just Z2 plus Z2. So in this case, the Galois group is abelian, and it's quite small. Okay, so much for this example. Now I want to finally come to the fundamental theorem of Galois theory, which is a relation between the intermediate fields of the Galois extension and the subgroups of the Galois group. So 1-1 correspondence. So this is the fundamental theorem. Of Galois theory. So this is a bijective correspondence between intermediate fields, so say subgroups of the Galois group L over K from a Galois extension L over K and intermediate fields. Of this field extension. So there is a bijection, so that for every subgroup, you can associate an intermediate field, and vice versa. Now, this somehow will allow to express problems about these field extensions in terms of problems in group theory. So you can you can solve a question about field extension, about solutions of polynomials in terms of something in group theory. But obviously this is not a magic wand. So sometimes maybe the problem in group theory will not be so particularly easy. I mean, it is not automatically that by this thing you can solve all problems, but at least it gives you a different way to approach a problem. And so we will look at some consequences later. Now let me first state the theorem. So first, I want to define, in some sense, what this correspondence is. So, so how do you associate to a subgroup an intermediate field, and how do you associate to an intermediate field subgroup? So, and I just give this definition. So first, how do I associate it to a subgroup an intermediate field? So let L over K be a Galois extension, right? Or it can just, in this moment, just be a field extension. And H, a subgroup in the Galois group of L over K, a subgroup. So the fixed field of H is fixed H, where obviously we kind of think that we remember who L and K is. It's just the set of all elements in L which are fixed by all elements in H. See, these are elements here are K automorphisms, so such that phi of A is equal to A for all phi in H. Note, if you remember, so first thing is, clearly this is a subfield of L, no? Because if you multiply it, add things, you have this. So this fixed H is a subfield of L containing K, because obviously every element of K is fixed by every element in the Galois group, so in particular by every element in the subgroup. And we also have seen, I have just reminded you at the beginning of this lecture, we have already shown that in one case we know what the fixed field is, namely if we take the whole Galois group. So we have shown that the fixed field of the whole Galois group is just K. No, because that's this was the result we had. It's precisely the set of all elements which are fixed by all elements in the Galois group. This is just K. This was, I reminded you of that at the beginning of the lecture. We can also, so I want to associate to a subgroup of the Galois group, I associate this fixed field. Now, conversely, assume I have an intermediate field. So if F is an intermediate field of L over K, so obviously I was a bit careless here. So here I said we have shown this, but we have it when this is a Galois extension. Here I have not made the assumption. So we have this if L over K is Galois. Otherwise this will not be necessarily true. No? We know, for instance, if you take a q square root, third root of 3, third root of 2 over q, the Galois group is the identity, and the fixed field is not q. It starts the whole thing. But if you have a Galois extension, and the fixed field is this is what we do. If F is an intermediate field, then we can look at the Galois group of L over F. So what is this? So this is a subgroup of the Galois group of L over K. So this is all the automorphisms of L, which the identity of K on K. And this certainly contains all the elements that are the identity on F, because F is bigger. In fact, the Galois group of L over F can be also just described as a set of all phi in the Galois group of L over K, such that phi restricted to F is equal to the identity. No? So this is a subgroup. So we want to associate to an intermediate field the subgroup of the Galois group, which is this one. Now this is a little bit, well, that's how it is and that's what we do. One could be tempted, one could think rather of looking at the Galois group of f over k. That somehow looks simpler. Instead of associating to f this one could try to associate this one. But this will in general not be a subgroup. I mean, there's no reason why this should be a subgroup of the Galois group of L over k. And at any rate, it doesn't work. So this is not the right thing. We want this. Okay. But I always in the final exam find somebody who doesn't do this, and so just wanted to point out that it's not the first thing that might come to mind. It's this one. Okay. So now I can state the fundamental theorem of Galois theory. So what is the statement? So I have introduced these two mappings. So we say let L over k be a Galois extension. So we have the two mappings, the two maps I introduced. The mappings. So on the one side we have here the subgroups of the Galois group of L over k. On the other side we have the intermediate fields of L over k. So we have two mappings, so we can either send the subgroup H to the fixed field of H. So in this case we have associated to a subgroup intermediate field, or we can take an intermediate field F, and we can send it to the the Galois group of L over F. So these are two maps. One goes from here to here, the other one goes back. And I claim these two maps are both bijections and they are inverse to each other. They are bijections, not inverse to each other. So obviously, concretely, one can directly say what this means. So that means if we take the fixed field of the Galois group of L over F, this is equal to F for all intermediate fields. F of L over K. No, that's one thing. If you go there, if you come from there and go back, then you get this. And the other statement is, if I take the Galois group of L over the fixed field of some subgroup H, this is equal to H for all subgroups. H of the Galois group. So we can go back and forth between subgroups and fields. It's just of this inverse bijection. Obviously, these bijections are inclusion reversing. So if the subgroup becomes bigger, the fixed field becomes smaller, and vice versa. So later on. Inclusion reversing. So that means if I have subgroup H1 is contained in H2, this will imply that the fixed field of H1 contains the fixed field of H2, and in the same way, if we have a field F1 which is contained, two intermediate fields contained in each other, then it follows that the Algebra group of L over F1 will contain the Algebra group of L over F2. So these two statements are obvious. No? So we don't yet know. So the real thing we have to prove is these two facts. But this fact is trivial. No? If I have a bigger group, then the set of things fixed by all element H1, will be bigger than that for H2 because we have just more conditions, and this is also obvious. No, the Algebra group of L over F1 are the elements, are the things which are the identity on F1. If F1 is smaller than F2, then there are more elements allowed here. So this is trivial. This is what we have to prove. And there's another part which is also trivial, which one just keeps for bookkeeping. That one knows that one has just the numbers. So the degrees. So this is just, if I take the degree of L over the fixed field of some subgroup, this will always be equal to the order of the subgroup. And if I take the degree of the fixed field of the subgroup over K, this will be the index in the Algebra group of L over K of the subgroup. So for all subgroups. Each of the Algebra group of L over K. You see that this is quite simple. We'll prove it at the end, but this is an easy consequence. And the same way we can say basically the same thing from the, instead of you arguing from the subgroup, we argue from the intermediate fields. So if you have an intermediate field, the degree of F over this intermediate field is equal to the number of elements in the Algebra group of L over F. And the degree of F over K will be equal again to the index in the Algebra group of L over K of the Algebra group of L over F. This is for all intermediate fields. But I mean, this part is in some sense more an exercise. I mean, I will say it, but there's nothing really there. Now we want to prove. So this was the first part. We want to prove part one. So basically, so in order to prove we have this mutually inverse bijections, we have to prove these two statements. Okay? And so let's try to do that. So let's start we first do the first one. Let F be an intermediate field. So we'll see in a moment that we essentially have already proven that. That's what I... Now, I claim that then L over F is the Galois extension. So L over K is a Galois extension by assumption. I claim also L over F is a Galois extension. Why is that? Well, we have that, so L is so L over K is Galois extension, so it's a splitting field. But L is a splitting field of some polynomial G in Kx over K, and thus also over F. So it follows that L over F is normal. Now, we also want to see that so we have to see it's normal and it's separable. So let F be the minimal polynomial some element A in L, say over F. So then we have to show that this has no multiple roots in its splitting field, or that it has so it has no multiple roots. So then it has no multiple roots in L, because as it is an irreducible polynomial with a 0 in L, it already splits. So L. So if it has no multiple roots in L, it has no multiple roots in its splitting field, and that's the condition for being normal. Okay. So F has no multiple roots. In F. Now that makes it separate. So so let now G be the minimal polynomial of the same A over K. Then we know that L over K is separable, so it has no multiple roots. G has no multiple roots. Multiple roots in L. But the minimal polynomial, so this is this F is a polynomial with coefficient in large F, which vanishes at A. G also vanishes there, so F will divide G. And so if G has no multiple roots, then also F has no multiple roots. Okay, so we just, okay, we could also have, if one doesn't like this argument, we could have assumed maybe we are in characteristic 0, so this thing with the multiple roots anyway doesn't matter, then it's just this first part that we need. But anyway, it's also no big issue here that we have, that the extension is always separate. So given this, we have that L over F is a Galois extension, and therefore thus L over F is a Galois extension, and thus the fixed field of the Galois group of L over F is the ground field F. That's what we have proven. Now, before the ground field was the field, we had the Galois extension L over K, and then the fixed field of the Galois group was K. But this holds for whatever the field is, so it's just that. So this we have proven before. So this shows this one direction. This one statement. The other statement is now more difficult, or at least I have to start it again. So we have to show that then we have to talk not about the fixed field, but about the so now let H be the subgroup of the Galois group of L over K. So when this is the Galois extension, we have to show that the Galois group of L over the fixed field of H is again H. So we put say F to be the fixed field of H, and so want to show that the Galois group of L by F is still this H. So now we apply the theorem of the primitive element to this to the original Galois extension L over K. So by the theorem, so here we really have to work a bit, theorem of the primitive element. We have that L is equal to K of A for some element, for some primitive element A in L. So there exists an element A such that L is equal to K. And we want to use this element. Namely, we write down a polynomial, which we will finally want to be the minimal polynomial of A over F. So you define F equal to the product over all elements in H of X minus H of A. So you know that A was our element here. H is an element in the Galois group, so it's an automorphism of L. It sends A to some different element. And we can take this product. Okay, this a priori is a polynomial in the coefficients in L. We multiply it out, the coefficients will be somewhere in L, where L is equal to K. So, as I said, we will be done once we show that, so our aim is to, so it's basically, yeah, maybe I should have said this. So maybe I can say this already here, because it's good to know what the strategy is. So, by definition, if I have an element in H, it will act as the identity on the fixed point of H, and it will be an element in the Galois group. So that means, by definition, H is contained in the Galois group of L over the fixed field of H. Because every element of H will is by itself an element in the Galois group, and it fixes the fixed field of H by definition. So in order to show that the two are equal, it's enough to show that they have the same number of elements. The number of elements in the Galois group of L over the fixed field of H is H. Actually, we only have to show one inclusion, namely that it's smaller or equal to H. No? Then, as this is contained in this, this then implies that the number has to be equal, and then they have to be equal. And we will show this. So basically, we will find if we have the minimal polynomial of A over F, then the degree of this minimal polynomial is equal to the degree of the field extension L over F, which is equal, as this is a Galois extension, to the number of elements in this Galois group. So if we find a minimal polynomial whose degree is at most the number of elements in H, we are done. And so the claim is that this will be our minimal polynomial. So we want to show, well actually, F is the minimal polynomial of A over F. I will again repeat why this is good enough. In fact, it's enough actually that it divides them. So obviously, if this is supposed to be the minimum polynomial of this over F, it had better be a polynomial with coefficients in this field F. So we first have to see plain F is a polynomial with coefficients in F. Now, if our it's just this here. So let's first see why this is the case. So first, maybe this is okay. So all the roots of F are in L are distinct because if H1 of A is equal to H2 of A, with H1 and H2 in this Galois group, then obviously then it follows it's the identity because L is equal to F of A, which just is equal to K of A, but also F of A, whatever, K of A. So if something is the identity on A, and by definition it's the identity on K, then it must be the identity. So, and now we want to see that the coefficients of this polynomial are in the field F. So we write F equals sum I equals 0 to some number. In this case, well, anyway, I don't need to know the number I next to the I. And so for an element, if I have an element L in H, we can compute the usual thing. L lower star of F. This is equal to the sum over all I, L of bi, x to the I. But I can also see this in terms of these roots. Because how do I, so the coefficients here are just certain products or sums of products of these roots. So if I apply an element in H to the coefficients, it's the same as if I apply this element to all the roots. So this is equal to the product over all H and H of x minus L of H of A. Applying this to the coefficients is the same as applying it to the roots. But now you see, so basically I've just made, so here I have the product over all H and H, L of H of A, but if I multiply everything by a fixed element in H, this product runs in the same way over all elements in H as it did before. No? Because multiplying by one element in the group is just a projection from the group to itself. So this is just the same as F. But that means, so thus, so this is almost done. So thus, we find that F is indeed, so F is an element in F of X. Because this says that, let me do it a bit slower. So thus, so we have that, according to this, we have for all I, bi is equal to L of bi for all L in H. So it follows that bi is in the fixed field of H, which was over F. And so thus, the polynomial F is a polynomial of coefficients in F. Okay. So now, so this is a polynomial with coefficient F, which has A as a 0. So thus, F and enlarged Fx with F of A is equal to 0. Thus, the minimal polynomial say G of A over F divides F. No?
Small f of A.
What?
Small f.
Yeah. Okay, that's maybe the problem of using the same letter, small and large, for different things. So therefore, the degree of this field extension, so of L over F, which is the same as the degree of the field extension F of A over F, is equal to the degree of this minimal polynomial. Now that we know it's a simple algebraic extension, which is smaller or equal to the degree of F, which is H. So thus we find that and this on the other hand is equal, as L over F is a Galois extension, we have the Galois group L over F. So the number of elements in the Gamma group is equal to the degree of the field extension. So therefore we have proven our statement. So we know that this group is contained in this group, but this group is smaller than this group, so they're equal. Okay, so maybe the easy part, 2 and 3, I will repeat and do next time. Also gives me occasion to state the theorem again, because we really want to do that. And then we see each other on Friday.